Morning everybody. Today I am going to tell you about the sulfur system, the phase diagram of sulfur system. As we all know that sulfur exists in two allotropic forms, rhomic sulfur and the monoclinic sulfur. And at 95.6 degrees centigrade, this rhomic sulfur at 1 atmosphere pressure changes to the monoclinic sulfur. Similarly, if we cool monoclinic sulfur to 95.6 degrees centigrade at 1 atmosphere pressure, it will change to the rhomic form. So this phenomena is actually known as polymorphism, and let me tell you about something about it. So polymorphism is the existence of the crystalline substance in two forms which differ in their physical properties only. And when this thing can occur in elements or in compounds, and when this occurs in elements, it is known as allotrope. So this sulfur shows two allotropic forms, rhomic sulfur and the monoclinic sulfur. And when we are discussing about the phases, as many allotropic forms are there, as many phases are considered to be present. Over to the sulfur system. This is the phase diagram for sulfur system, and as we all know, it is a one component system. Various phases which exist in the sulfur system are the two allotropic solid states, that is the rhomic sulfur and the monoclinic sulfur. Then we have the liquid state, sulfur liquid, and another one is the vapor state. This we have represented as Sr for rhomic sulfur, Sn for monoclinic sulfur. These are the two solid states. And then we have the vapor state, which I have represented by Sv, and we have the liquid state, which has been represented by Sn over here. For easy representation, I have taken these symbols. So as we can see, this is the phase diagram for sulfur. This is the solid phase. Here is the vapor state, and here is the liquid state, and this is for the monoclinic sulfur. Now I will tell you about the salient features first of all. We can see that we have a curve OB, we have the curve OA, we have the curve AE, we have this curve OC, we have this curve AC, and we have the curve CN. Along with all these curves, we are having triple points, various triple points, as well as metastable equilibria is also present over here. So let's start with taking curves first of all. Just see this curve OB. This is actually the sublimation curve of rhomic sulfur, and at this point O, rhomic sulfur will change to the monoclinic form. It will this is the transition temperature, and this will transition to the monoclinic form. The rhomic sulfur will get changed to the monoclinic form at 95.5 degrees centigrade. So at this point O, it will change to the monoclinic form. So this curve OB, this gives the sublimation curve of rhomic sulfur, and the two phases in equilibrium here are rhomic sulfur and the vapor phase of the sulfur. So Sr and Sv I have written over here. So these two phases are in equilibrium along this curve, and this curve represents the vapor pressure, the effect of pressure on vapor pressure on the and the temperature is shown by this curve. So if we calculate the degree of freedom along this curve, we have one component. We can go by this equation. Since it is a one component system, the number of phases which are in equilibrium are 2, and at this they are Sr and Sv. So phases will be 2 and plus 2, and F will come out to be 1. This means that the degree of freedom is 1, and it is univariant along the curve. The OB, the system is univariant, and the degree of freedom is 1. Now let's see, this rhomic sulfur has been converted to the monoclinic sulfur at this point O. Now this OA, this represents the sublimation curve of the monoclinic sulfur. This is the effect of vapor pressure on the monoclinic form of the sulfur. This is represented by this curve OA. And the two phases which are in equilibrium along this curve will be the vapor phase and the monoclinic phase. So SM and SV. I have written it over here. Curve OA is SM and SV are in equilibrium with each other, and just now as we have calculated the degree of freedom in the case of OB, here also the degree of freedom will come out to be 1. This means that the system is monovariant along the curve OA. If we fix one variable, the other variable will be fixed. At point A, now this point is actually the this point is actually the melting point of the monoclinic sulfur, which is 120 degrees centigrade. At this point, the monoclinic sulfur will melt, and we will have the liquid phase now. And this is also a triple point, and the three phases which exist here are monoclinic sulfur, vapor, and the liquid. This I will tell you later on. I will deal with all the triple points together. So when we consider this OA, we have seen that it is a one component system. Similarly, now we come to AE. At A, all the monoclinic sulfur means the solid form of sulfur changes to the liquid. So this curve AE, it represents the vapor pressure curve of sulfur, and the two phases in equilibrium are the liquid sulfur and the vapor sulfur. Just have a look over here. At A, the two phases are the liquid and the vapor sulfur, and as just now we have calculated, and when we will calculate the degree of freedom over here, since there are two phases, F will again come out to be 1. This means that if we fix one variable, the other variable will be automatically. One more thing over here, the 1 ATM line means the 1 atmospheric pressure line cuts this curve A at this point when the temperature is 444.6 degrees centigrade. So this is the boiling temperature of sulfur, where 1 ATM line cuts the vapor pressure. So this is the boiling temperature 4.6 degrees centigrade. This curve ends at E. So E is the critical temperature, you can say, beyond which critical phase will exist. Now let's see this curve OC. As we can see, here we are having the rhombic sulfur, and here is the monoclinic sulfur. And this curve, this represents the transition curve of sulfur, when the rhombic sulfur changes to the monoclinic sulfur. And this curve, it represents the effect of pressure on the transition of sulfur. This curve OC, it represents the effect of pressure on the transition of sulfur. And as we can see, this curve OC, it is inclined away from the pressure axis. So we can say that it is having a positive slope, and dp upon dt from the Closius electron equation is positive over here. And the two phases which exist in equilibrium here will be the rhombic sulfur and the monoclinic sulfur. This is rhombic sulfur and the monoclinic sulfur. These two phases exist in equilibrium with each other, and so as we have seen earlier also, if we calculate the degree of freedom means F from this formula, that will again come out to be 1. This means that the system is univariate along this transition curve. Now let's take this curve AC. We have seen that at point A, this is it starts changing. So this point AC, along this curve, we are having the monoclinic sulfur and the liquid sulfur in equilibrium. Again, the degree of freedom will come out to be 1. So the system is univariate along this curve. Now comes this last one, CF curve. CF curve, it is actually, we are having the rhombic sulfur that side and the liquid sulfur that side. So actually it is the fusion curve of rhombic sulfur. This is the fusion curve of the rhombic sulfur. This was the fusion curve of the monoclinic sulfur, and this is the fusion curve of the rhombic sulfur. And the two phases which are in equilibrium along this curve are the rhombic sulfur and the liquid sulfur, and the value of degree of freedom will come out to be 1. This means it is univariate along the curve. So we have dealt with all the curves over here. The curve OB, OA, AE, AC, OC and CN. So in total these are the curves, and all along the curve, since it is a one component system, two phases are in equilibrium, the degree of freedom comes out to be 1. Now let's take the points. We see this point O. Which phase is present over here? The rhombic sulfur phase. Which phase is present over here? The vapor phase. And what is here? This is the monoclinic phase. So, how many phases are in equilibrium at this point O? 3 phases are in equilibrium. So, it is termed as the triple point. So, this is the triple point, and the 3 phases in equilibrium are the rhombic sulfur, the vapor sulfur and the monoclinic sulfur. These 3 phases are in equilibrium over here. So, when we calculate the degree of freedom from this equation, what we get is F is equal to C minus P plus 2. Here the number of components is 1, we have seen, so F will be equal to 1 minus number of phases which are in equilibrium are 3. So it will be minus 3 and plus 2. That comes out to be 0. So at triple point, the degree of freedom is 0 and it is a fixed point. This means it is a fixed point. We don't have to fix either temperature or the pressure. All the 2 variables are fixed. Similarly, we have the point. Similarly, we are having this point A. This point A. Here we are having this vapor phase, liquid, and the monoclinic sulfur. And all these, the 3 phases in equilibrium are SM, SL, and the SV. And similarly, when we are here to calculate the degree of freedom, we will find the system is non-variant at this point. Means we don't have to fix neither the pressure nor the temperature. They both are fixed between 120 degrees and 0.025 mm of Hg. So this means that the system is non-variant at point A. Similarly, we have the point C. We have the point C, which shows the equilibrium between the 3 phases: monoclinic sulfur, the liquid sulfur, and the rhombic sulfur. Similarly, when we will calculate the degree of freedom over here, we will get 0, means the system is non-variant. So, in fact, the sulfur system has these lines, six curves. It is having 6 curves, 1, 2, 3, 4, 5, 6 curves. There are 3 triple points and there are these 4 areas. One more thing I have to tell you, that all the 4 phases of sulfur system do not coexist together at any point. Only 3 phases can exist at any point, because if there are 4 phases in equilibrium at any point, then when we will calculate this value of F, then that will come out to be -1, which don't hold any meaning. So in the sulfur system, the 4 phases never coexist together. Only 3 phases are present at any point, and that happens only at the triple point. Along with this, we are having the areas. In this diagram, you can see we are having the areas. Like this is the area 1, vapor, upper vapor. Area below BOAE. This is the vapor area. We have this liquid area FCAE, and then we have this COB area. This is for the rhombic sulfur, and we have this area enclosed by COAC. This is for the monoclinic sulfur. And since in the areas we are having only one phase present, and as one phase is present, then the system will be bivariant. If we calculate F from this, we will find that it's a one component system, 1 minus 1 plus 2, and the value comes out to be 2. This means in the areas we have to fix both the pressure and the temperature in order to explain the system. Now, just as you have seen in the water system and carbon dioxide system, also there is a meta state, and here also we find the metastable equilibrium. Now at this temperature 95.5 degrees centigrade, first of all let me tell you about the metastable curves. Which are the metastable curves? We see this dotted lines is OD. OD is one of the metastable curve. Then one curve is this DC and one curve is this AD. So these are the metastable curves, and there is one metastable triple point also which is at D. Now I will explain them one by one. Since we have seen that this is the transition temperature, means at this temperature the rhomic sulfur will change to the monoclinic form. The rhomic sulfur will change to the monoclinic form, means one form of sulfur will change to its another allotropic at 95.5 degrees. So there is like molecular rearrangement, but if this heating is done very rapidly, then it may happen that the rhomic sulfur may not change to the monoclinic form, but it may change to its liquid state. At this point, it is in metastable equilibrium. The rhomic sulfur will not change to the monoclinic form, but it will be in its metastable equilibrium with the liquid. So this dotted curve OD, it actually represents the metastable equilibrium between the rhomic sulfur and the vapor sulfur. And if you calculate the degree of freedom here, that will also come out to be 1, means the system is univariate around the curve. And another metastable equilibrium is this point A. It is actually the melting point of monoclinic sulfur. But suppose we cool it in such a way, we cool the sulfur in such a way that it does not gets transformed to the monoclinic form, then a metastable equilibrium is established between the vapor phase and the liquid phase without appearance of the monoclinic phase. So this point AD, it again represents a metastable equilibrium. It is again a metastable equilibrium where the liquid sulfur is in a liquid metastable equilibrium with the vapor phase. Now another metastable equilibrium is here. You can see along the curve DC. Along the curve DC, we have the metastable equilibrium between the rhomic sulfur and the liquid sulfur. The rhomic sulfur is in metastable equilibrium with its liquid form, and here also if we calculate the degree of freedom, that will come out to be 1. So the system is univariate. Now let's come to the metastable triple point. This is the metastable triple point. Here the 3 phases are in metastable equilibrium with each other, and these 3 phases are you can note it down also. The 3 metastable phases are the rhomic sulfur, liquid sulfur and the vapor sulfur. These 3 phases are in metastable equilibrium with each other at this point B. And as we have calculated earlier, the degree of freedom here will come out to be 0. Means the system is non-variant at this point D. So that's all for the one component systems. I have told you about the water system, about the carbon dioxide system, and today was the sulfur system. So with this, the one component systems is over, and next time I will tell you about the 2 component systems, and under which there are the systems having congruent melting point and the systems having the incongruent melting points. So thank you very much for today.